Again, good morning, and let's continue with our lecture series. So we'll get to lecture number 3. And as you can see on the schedule, the lecture number 3, now that we have covered fundamentals of sensing, particularly the interface controlled or granular type sensor, resistive or semiconductive type sensor. We're going to talk about one specific case as a case study, a carbon monoxide sensor, how to fabricate, how to test, etc. So with that, let's proceed. And typically these sensors are made by thick film technology or screen printing. So I give you some references as usual. And this particular reference will be actually that it talks about 3 different types of sensor that we made and tested in actual digital engine exhaust system as a test bed. So if you make a bulk type sensor, which you can, but it requires a lot of power. So if you want to take a bulk type sensor and heat it up to 300 or 400 degrees C, where the sensors are active, you need large power requirement, heated by iridium, palladium, or chromium alloy type wire. You can see the bulk type design of sintered tin dioxide sensor heated with palladium iridium wire, and the other palladium iridium wire can be used to detect the change in resistance of the material. Or you can make a sintered tin dioxide which is hollow and can be heated by radiation heat to, again, an electrical coil. Obviously, the power requirement here would be lower than power requirement there in this case. But nonetheless, this will require hundreds of milliwatts of power. So what is desirable is that you make sensor, minimize the mass by using the thick film technology or screen printed technology, and where the power requirement can be less than 200 milliwatt. So again, you can see the actual sensors. You can see the size. It's 1 by 2 millimeter type sensor with this gold pads. You can see 2 for heating and 2 for measuring resistance changes. You can see the size of this sensors, and these are usually printed on printed on top of an interdigitated gold electrode on a piece of alumina. You can see at high magnification, you can see the gold fingers in that sensor. So it will require, if you really want to lower the power requirement, you can go to thin film technology and create thin film sensors. One of the sensor actually goes into this device through which you can blow. It takes your breath sample when you blow through it, and it will detect the alcohol content in your breath. And this is used by traffic police in Korea, for example. So what is thick film technology? It's known as screen printing as well. So there is screen, which is made of stainless steel or polyester or nylon screen attached with proper tension to a stainless steel frame. Then you can cover, if you want to print particularly a patterned device, you can cover the entire screen with UV sensitive photo emulsion, and then you can use a mask through which you can shine UV light to create that pattern, replicate that pattern on the screen, and then you can use that patterned screen to print your device. In terms of substrate requirement, there are some generic requirement, but in general, you need good thermal coefficient matching between the film and the substrate to avoid microcracking, good mechanical strength, thermal shock resistance, good electrical resistivity. The rule of thumb is that since you're measuring coating which is sitting on top of the substrate and the electrode is in between the substrate and the sensor film, your electrical resistivity of the substrate has to be 3 orders of magnitude higher than the film. So in terms of screen specification, you can buy screen by specifying the mesh number. The higher the mesh number, the finer the screen is. And you can see filament diameter that makes the screen, percent open area, typical wet print thickness that you can print through these screens. And there are multiple choice of substrate material: alumina, beryllium oxide, aluminum nitride, and silicon carbide. This is the material of choice because you can make alumina very inexpensively, and an insulator. These are all insulators, by the way. You can see the resistivity values at room temperature. But the other consideration are obviously coefficient of thermal expansion, and obviously silicon carbide will have better match with silicon technology compared to some of these oxides. But thermal conductivity wise, some of these materials are more attractive than alumina, but this is still a material of choice because of the cost. And you can make alumina inexpensively in bulk form, like sheets of alumina, using this so-called green tape casting technology. Whereas beryllium oxide is not desirable from the environmental point of view. It's health hazard. Beryllium, when intact, it's okay. But if it chipped or you create nanoparticles of beryllium oxide, it's dangerous for our health, for our lung condition, for example. Aluminum nitride processing is very expensive. You have to sinter this material in nitrogen environment, and it takes longer because the sintering temperature cannot exceed the decomposition of the material. And the silicon carbide oxidation can be a problem. So if you're using silicon carbide as a substrate in an oxidizing environment like in air at high temperature, then silicon carbide would oxidize. So alumina is still the material of choice as a relatively inexpensive and substrate with desired properties. In terms of screen printing process is very simple. You take an ink, and we'll talk about how to make an ink, spread it on the screen, and your substrate is sitting underneath, and then you're going to squeeze this ink through the screen, and during squeezing ink viscosity will go down and flow through the screen and print a film on the substrate. If you take actually a closer look, and I'm exaggerating here, but it's not going to be continuous immediately after printing. So you'll basically have dots. Then these dots have to connect. So you need the viscosity in a range for some time after printing so that you get lateral motion to connect the dots. And eventually the driving force for making a kind of uniform film is to decrease the surface area. So we will get a film, wet film, that will look something like this. And then we'll talk about how do you know what wet film thickness you have to print to get to the dried and fired film thickness that you desire. After we're done printing, then we usually go through a drying process and a firing process where we ramp up to a desired temperature. Typically for a lot of the oxide, you're talking about firing in the range of 600 to 1000 degrees Celsius. And you hold it there for some time and then cool it down. So again, this is an idealized kind of firing process of the film. So here is an example of a very sophisticated screen printer. You can see the frame is attached here, the screen, and then there is a squeegee, that red rubber piece here is the squeegee. The ink is loaded into this pen, and then it's, you can control the pressure with which the ink will come out and spread it on the screen. You can control the squeegee pressure of the squeegee automatically, and then you can control, so your sample substrate will be sitting here that can be pushed. So in that case, your substrate will be just underneath the screen, and you can adjust the snap of distance, the Z direction distance, and XY positioning, and you can look under microscope to see the alignment of the substrate for screen printing. Or you can buy a tabletop screen printer, something like this, less expensive than that, but you can sort of control the squeegee pressure and ink deposition and etc. by nitrogen pressure from a nitrogen cylinder. So it's not as sophisticated as the other one, but it works pretty well. So in terms of the substrate that I talked about, so here is a piece of alumina where you create this interdigitated gold electrode by screen printing, and you can create the mask. And you can see in CAD, CAM, you can draw this, and you can specify the width of the finger, you can specify the distance between finger, and then you can screen print using a gold ink through a mask that looks something like this. And it comes with two holes, and this one set of fingers will be connected to this pad. The other set of fingers will be connecting to that. And you can attach your lead wire through these holes and connect those lead wire to the measuring device. Here are some other designing, in this case, if you look at the specification, the finger width was about 250 micron, and the distance between fingers were also similar order of magnitude, 250 micron. In the lab, we have made other designs using platinum ink, for example, for high temperature applications, a circular electrode, this zigzag type electrode, and so on. So we make different kinds of, sort of sensing platform to do measurements. There are all kinds of defects and faults that you can create during screen printing, and I'm not going to go through the details. I copied this from the source that I gave you on page number 1, references. But the pre-definition faults depends on machine variable, like faulty screening, or snap of distance between the substrate and the screen, too high or too low, squeegee pressure, attack angle, at what angle the squeegee will come and strain the ink, and also in the ink or paste rheology, viscosity. Now, you also can get all kinds of faults in the printed film, too thick or too thin or uneven thickness. And again, it will depend both on machine variables. Over thinning can be an indication of low viscosity or effect of temperature. So there are both machine variables as well as ink property that will define or that will create different types of thickness faults in the printed film. So let's talk about how to make this ink that we use for screen printing film. Obviously, you're going to mix your inorganics like sensor material, sometimes added with glass prints for adhesion purposes or for selective detection, you add catalyst. Mixed with organic vehicle, a typical organic vehicle is conductor gold or silver with some solvent, and you create the ink. Ink has to be non-Newtonian in terms of requirement of viscosity. So viscosity will depend on straining rate. So for example, it has to be thixotropic during settlement and so it should be high viscosity at low strain rate. Also, it should be pseudoplastic, meaning it should decrease in viscosity at high strain rate. And this is particularly during the flow or squeegee operation on the screen. So in terms of viscosity ranges, you want viscosity roughly to be of the order of tens of pascals second during straining rate of 1,000 per second. And this is typically the strain rate when the squeegee is traversing on the screen. Then after printing is done, you want the viscosity of the ink to go up in this range for a small amount of time where you get the leveling. Remember, there has to be lateral movement to connect the dots, isolated dots that you typically get after printing. And the straining rate there is controlled by the surface tension. The film is still weight, and the straining rate is of the order of 1 hertz. And after leveling, you want the viscosity to go up so that you don't get to bleeding type, so flowing all over the place. So you want the viscosity to go up, and the straining rate there is under the gravitational force, very low straining rate. So this gives you a ballpark range of viscosity that you need to target. So the viscosity can be controlled by the amount of the solid that you add, their size, their shape, the electrical charge on them, and the additives like surfactant and weighting agents that you can add to your ink. So if you look at the typical viscosity values, so this is just your ink that you stir for uniformity and so on. And then high viscosity ink. And this is the squeegee that is straining the ink on the screen. And you can see the viscosity drops sharply. And it helps flow the ink through the screen. And after you've done screen printing, then you get leveling. So the viscosity increases, and you get leveling range to connect the dots, and then eventually it increases so that it doesn't flow any further. So you can avoid bleeding type behavior. In terms of electrical conductor material, you have all kinds of choices. Obviously, we use noble metal for the reason that is obvious: silver, gold, and platinum, and palladium. There are various parameters: resistivity value, sheet resistivity, melting point, thermal expansion coefficient, and particularly the price. If you take silver as unit price, gold is going to be more expensive, and platinum will be even more expensive. So you can use other metals as electrode like copper, molybdenum, and so on, and price-wise they look very, very attractive. But then the problem would be oxidation, for example. So there are a couple of issues. So among noble metal, silver seems to be best choice for low temperature particularly. But there are two problems with silver. There's the migration of silver under electric field, particularly in humid environment. And the problem has been solved by readily dissolving in molten metal. So you basically create a solder material, which is tin lead alloy. You can see the composition of the, what I meant is that instead of pure silver, you use an alloy that can prevent dissolution of the solder material into the electric conductor. So even though you use the silver lead alloy as the conductor, but it has better resistance in terms of dissolution of the solder material, less solubility of this into the alloy as opposed to pure silver. The problem with copper, though, is the oxidation problem, and you have to be careful about the Ellingham-type diagram where if you cross this boundary in terms of oxygen content, depending on the temperature, most of this metal, including copper, will oxidize. So that's one of the reasons why copper is not such an attractive electrode material, but silver, gold, and platinum are. In terms of the weighting behavior and the thermodynamics and the rheological behavior of the ink, so it's controlled by the so-called contact angle. It's controlled by interfacial energies in the ink, and you can get wetting or non-wetting behavior depending on the contact angle. So if the contact angle is between 90 and 180, it will be non-wetting ink on top of the substrate, not desired. You actually need a wetting type ink where the theta has to be between 0 and 90. You get wetting behavior, but if it's too low, if it's close to 0, you get a spreading and it will bleed out and so on. So you really need the contact angle to be controlled between 0 and 90 degrees. You can see the contact angle depends on all kinds of surface and interfacial energies. And you can actually control those energies to some degree. So you can add additives like surfactants and wetting agents to control these interfacial energies that will lead, for example, adding surfactants will reduce the gamma between solid and liquid, helping further decrease theta. But you have to be careful that you add optimum amount so that you don't decrease this gamma so low that theta becomes very close to 0. That will lead to bleed out. So there is some compromise of how much you should add to control the theta. Other parameters that you can use to control the viscosity is the size, the amount you add, surface charge, shape, etc. So you can see here is an example of using two different size particles, 750 micron and 175 micron size particles of a given material as a function of the straining rate. You can see at lowest straining rate, viscosity varies. Viscosity variation can be substantial between the two. But as you go to higher straining rate, you can overcome the size effect. The particle-particle interaction are weak forces, so the effect is dominant at low straining rate and not so dominant at high straining rate. Or you can control the particle size. So if you use mono-sized particle, as opposed to mixed particles, 2 different sizes, 3 different sizes, you can see that viscosity keeps on decreasing for a certain volume fraction of the particle. Monosize will give you, large size will give you higher viscosity, monosize, I should say. compared to multi-size, lower and lower viscosity. Because you get easier flow with multi, large range particle size. So you can actually use the optimum mixture. So here is large size particle versus small size particle viscosity. And then you can mix the two, and you can see the viscosity keeps on decreasing, and it reaches some minimum viscosity in certain volume fraction addition. So you can control the mixture of the two to target certain viscosity. This is clear, obviously, as you add more and more solid, your viscosity will go up. So you can always add solid to your ink to increase the viscosity. Surface charge that you can get in colloidal solution, where you have your solid particles suspended in a colloidal medium, you can get surface charge you can measure by so-called zeta potential. So we look at the viscosity, and this is a log scale as a shear stress, strain rate, if you wish. Then you can see that at low shear rate, the surface charge on the surface of the particle will make a huge difference in viscosity. But when you go to high strain rate, this Coulombic interaction coming from the charged particle can be minimized, and the viscosity difference is not that great. Obviously, irregular shape type particle will give you a higher viscosity than a regular shape particle. That also at high strain rate doesn't make a big difference. The shape of the particle can also control the viscosity, and you can see that as opposed to the regular shaped spherical particle versus plate-shaped particle, you can get much higher viscosity at low strain rate compared to these. But then as you increase the shear rate, the behavior can completely reverse. Now you can see that this aligned platelets is giving you lower viscosity than this spherical shape particle. So these are all the considerations that you have to take into account to optimize the viscosity of your ink. And next, I'm going to talk about the bonding effect, bonding of the film to the substrate. There are three types of bonding mechanism that is used, so-called reactive, flux bonding, and frit bonding. And the reactive bonding, the idea is to add a small percentage of reactive oxide like copper oxide or cadmium oxide that will react during firing with the substrate like alumina and form copper aluminate spinel or cadmium aluminate spinel that keeps bonding. It's basically going to pin your film at dispersed location and give you bonding, improve the bonding of the film to the substrate. There. Flux bonding is another approach where, again, a small fraction of the flux material like bismuth oxide that is added as a flux to the ink. And then there is a eutectic, for example, between bismuth oxide and aluminum oxide at around 800 degrees C. So if you heat treat or to fire the material around the eutectic temperature, you can actually make a eutectic melt that will create chemical bonding of the film with the substrate. And finally, the frit bonding is the most popular one that is used in the industry. So you add, again, small fraction of a glass frit, and when you use, at the softening temperature heat treatment, The glass will soften and will interlock. That softened glass will get into the surface rough area of the substrate and make a mechanical interlocking, and that way you can get bonding. So these are the three different types of bonding that one uses, but the industry uses primarily the glass-free bonding, I talked also about the connection or correlation between the wet thickness versus final fired thickness, and you can do some modeling or you can do some analysis. So the thickness of the wet film is given by this equation, where this is the thickness of the emulsion. That is, if you are using a patterned screen, there is a certain thickness of emulsion on the screen, and that's that. If you don't have any emulsion, you can take this out. The other parameters that control the wet thickness depends on screen cloth thickness that is known, percent open area that is known, and the screen retention factor that is controlled by both machine variables as well as property of the ink. And the wet thickness is related to the final fired thickness by this relationship, where Vs is the volume of the solid fraction in the ink, which is something that we know. Something that we don't quite know without doing experiment is the fraction of fired film porosity. What is the percentage of porosity in the fired film? That's something we have to do on our film by doing microscopy. We fire the film, do microscopy, and figure out the percent or fraction of film porosity. And once you know that, then you can clearly use that given certain wet thickness, what should be the final fired thickness. And you can see that this parameter, so-called retention factor, depends on both ink properties as well as machine variable. If you make a tacky or sticky ink that gives larger S, that can always be decreased by adding organic additives. You don't want S to be large because that will be sticky ink. That's something you don't want. Or it depends on machine variable. S can be controlled by machine variable like surface tension of the screen, snap of distance, squeegee speed. And increase in these will decrease S and increase wet film thickness. So there is some, science that has been put behind prediction of fired film thickness based on the initial wet film thickness. Here I'm showing some examples of various devices that are typically made by this screen printing or thick film technology, and we, there are many other devices that people make, but it's just a partial list of devices that are made. So I'm going to talk, about the sensor that is made by printing the film of the sensor on top of an interdigitated gold electrode that is printed on aluminum substrate. And we position this sensor inside a furnace where we can control the temperature of the furnace, and gas concentration can be controlled by mass flow control system by passing a single gas or mixture of gases. And then data can be collected by measuring with a multimeter and connected to a desktop for automatic data collection. So here is an actual setup in a lab. So this is the furnace that I'm talking about, where temperature can be controlled. There is a quartz tube where the sensor will be inserted inside this tube, and the gas is flown by controlling through mass flow control system into that quartz tube. And then the sensor holder looks something like this. So this is the tip of the sensor holder. Sensor can be attached something like this, with the gold lead wire coming through the hole in the quartz tube. And this is the back of the probe, sensor holder, back of the sensor holder. That will fit into this quartz tube and give a gas tight seal. And then the lead wire will come out to the back side of the probe that gets connected to the DAC system that collects the data automatically. And this can be, the flow and mixing ratio, the temperature of the furnace can be controlled remotely from a lab or from a dorm and collect the data continuously. So here is actually a setup that was created in Professor Hasib's lab in the University of Malaya. And this can be duplicated. In fact, I have some pictures of his actual setup with the tubing and positioning of the mass flow control system and design of the quartz tube, inlet of gas and outlet of gas. So this can be duplicated here if that is desired. With that, I'm going to move on to actual sensors made in our lab based on TiO2. This is a CO sensor based on TiO2, and what I'm showing here, the response, measuring resistance value from the sensor, plotted as a function of CO concentration. So these are the 90% response values at each concentration of CO. And I'm showing the data at two different temperatures, both in the forward direction and in the reverse direction. Forward meaning that when the CO concentration is increased, and the reverse direction would be when the CO concentration is gradually decreased. And you can see in both temperature, 600 and 700, they are on top of each other. That means you are getting practically completely reversible, completely recoverable sensor, which is expected. Because remember, your target gas is interacting with the surface adsorbed oxygen. It's not changing the oxide. It should be, in principle, should be completely recoverable. And you can see that we're reaching the saturation level as you keep on increasing CO. And the saturation level is achieved when all the surface adsorbed oxygen are consumed by CO. So even if we increase the CO concentration, there is no more surface adsorbed oxygen to react with. So if you want to increase this range of sensing, then one has to use high surface area material like nanoparticles and nanostructures. So we actually end up testing one of our sensor probe in real automotive engine that is tested at CAR in our mechanical engineering. CAR stands for Center for Automotive Research. And this facility also comes with an on-board HORIBA analyzer that can help compare our sensor response with the HORIBA analyzer to make sure that we are measuring the right concentrations. And our sensor is positioned next to the lambda sensor. The temperature around here is about 600 degrees C. So this is what we do. And to show you some of our probe, so here's a screen printed sensor with two probes for measuring the resistance change. And there is a thermocouple to monitor that is, so this sensor doesn't have a back printed electrode for electrical heating. So we have to monitor the actual temperature of the sensor using thermocouple. So you can see the actual package one, so then we cover it with ceramic tube like alumina with a slit for the gas to get in. You can see even with the slit, the protective layer gets blackened by carbon soot in the end. So the engine environment is really a very dirty environment. Or if we can use, there's another design where we put our sensor inside this stainless steel housing with holes. The gas would get access to the sensor through these holes. And we have, in fact, in this publication, we find out that we have made this type of probe for CO2 and NOx, and we have tested in this automotive sensor testing environment. So with that, I'm ready to conclude this lecture, and we will continue with our future lectures, and we'll move on to the electrochemical type sensor, again, first with the fundamentals, and then we'll move into some case study of making a particular electrochemical sensor. So I'll see you in the next lecture.